we can slowly start. Hello everyone, and welcome to the fourth talk of this series on equilibration and thermalization of a summer colloquium series at Washington University in St. Louis, organized by Alexander Siedel and myself. Today we have the great pleasure of having Professor Peter Reimann with us, talking about the foundations of statistical mechanics in and out of equilibrium. Professor Reimann is one of the most illustrious scholars and scientists working on this topic. He got his PhD at the University of Basel and had postdocs around Europe in Germany and Hasselt University in Belgium and in Budapest, and then has become full professor at the University of Bielefeld. I must say I'm particularly happy because I really admire Professor Reimann's work. It has had a profound influence on some of my work, so I'm very looking forward to hearing today's talk. And so you have the floor, Professor Reimann. And before we start, regarding questions, Professor Reimann is happy if you just come up with questions and just speak up. Otherwise, you can write them in the chat and I will sort them out and interrupt Professor Reimann when it's the case. So, okay, you can start, Professor.
Yeah, thank you very much. I am very glad for this opportunity and honored to talk here. And I enjoyed very much the previous talks. And I hope we will also profit a little bit from this talk. Just not in order I don't forget, this is the funding. This is in the context of a collaborative research unit together, Bielefeld, Oldenburg, Osnabrück, and Jülich. We have a little research unit on practically exactly this topic of my talk. So welcome everybody. For most of you it is almost early in the morning and it is in the middle of holidays, so I am very glad that some people came anyway to this talk. So let's, oops, it was not on. So let me start with some of the still unsolved fundamental problems in this field of statistical mechanics in and out of equilibrium. So the setup is as follows. We imagine, as usual in textbook statistical physics, we are dealing with macroscopic or so-called many-body systems with many degrees of freedom. For instance, the usual examples, a gas, a liquid, a solid, or some more specific spin models, and so on, as you know it from statistical physics. And they are supposed to be isolated from the rest of the world. So you have an autonomous system. And you know, the microscopic dynamics has the property of being time reversible. So here is a very simple example. Two particles will scatter, and then they make a certain scattering trajectories. And if you would make a movie of this event and show you the movie backwards, it would be a perfect solution of the equations of motion as well. Everything can happen backward in time, microscopically, but macroscopically, the macroscopic behavior, which you may call thermodynamics, is known to be irreversible due to the second law, for instance. So if you have here a gas through a little hole, this is an irreversible process. You will, if I show you the movie in the wrong direction, you will immediately notice that this is impossible macroscopically. So that's a first question, how to reconcile these things. The microscopic dynamics is very complex and sensitive, chaotic. here I have moved the initial position of one of these particles a little bit downward, and then the scattering event is completely different, and the subsequent scatterings will also be very different. And after a few scattering processes, the whole dynamics has nothing to do anymore with the previous unperturbed dynamics. But the macroscopic behavior is very simple and robust. If I change here the position of one molecule in this box, the same thing will happen. And this will follow very simple laws, this effusion process. And it's very easily reproducible in an experiment in spite of this microscopic sensitivity. How to reconcile these two things? And then the system is isolated. Many complicated things happen, but certainly all these molecules will never come to a rest. The motion goes on and on forever. But the macroscopic behavior seems to show a relaxation towards some steady long-time behavior, which we call thermal equilibrium. And moreover, we know from textbooks and experiments, this long-time behavior can be very well described by the so-called microcanonical equilibrium ensemble. How to reconcile these two things? Or differently speaking, how to explain all these macroscopic features from the microscopic behavior. That are some of the unsolved fundamental problems. Of course, these questions have a long history, going back to Maxwell, Boltzmann, and von Neumann was the first to address them in a quantum mechanical context. Many people privately think they have the solution to these questions, but I think one can say generally they are still considered as not satisfactorily understood, these basic questions. In this talk, I will focus on quantum systems. In the previous slide, maybe you thought this is classical, but from here on, I will focus on quantum systems and on a few basic issues. This is a big field and I cannot cover everything. This talk is more like a personal overview or review. I address a few issues which I consider particularly interesting and where I can say something at last. It is not an overview of the field and I will not tell you the latest news in this talk. It is more like a personal review, so to say. And I will omit many things. For instance, I will not go into any details regarding some special systems. I will focus, so to say, on generic systems and omit special systems, for instance, exhibiting so-called integrability or exhibiting sufficiently much disorder so that giving rise to many-body localization or so-called many-body quantum scars and so on. And many special things will be omitted, like phase transitions and all and classy systems. I focus on simple generic systems like in textbook statistical physics. I will also not go into any numerical detailed methods and also not address experimental issues. So that is the general framework. Now, setting the stage and the notation is essentially just textbook quantum mechanics. So we use and we work with basic non-relativistic quantum mechanics for isolated systems. So they can be modeled by some many-body Hamiltonian H, which is time independent because it is isolated, which models some simple gas or liquid or solid or some spin lattice model or Hubbard model and so on. A generic many-body model. I suppose the system is large, but not infinite. It is still finite. You have a finite number of degrees of freedom or of particles, and you have a finite spatial extension. It is not infinitely large, just large. That is the restriction. And then you can say, usually this Hamiltonian will have a discrete spectrum of eigenvalues, En, going from 1 to some large but finite upper limit or to infinity, depending on the specific model you are considering. And then the corresponding eigenvectors to these eigenvalues, they span the system Hilbert space, your model Hilbert space. These are the eigenvectors of your Hamiltonian. And any pure system state can then be expanded in this energy eigenbasis with complex coefficients Cn, which are normalized. For simplicity only, in this talk, I focus on pure states and I omit mixed states. Everything could be done for mixed states as well. That is all very easy. And the observable quantities are modeled as usual by some self-adjoint observables on this Hilbert space, giving rise to expectation values. If the system is in state psi, this will be the expectation value averaged over many repetitions of the experiment. So now let's turn to the dynamics. How do these states change in the course of time? Of course, they change according to the Schrödinger equation. This governs the temporal change of psi. And here appears your Hamiltonian from before. That governs the dynamics, the time evolution. And why does it not? Okay. Now, if you give me the initial condition, which is some state psi of 0, which can be expanded, as every state can be, then the solution of the Schrödinger equation is this. You can easily check. This is the solution of this equation, satisfying this initial condition. So essentially we are done. Of course, that is just a formal solution. You need to know the explicit values of the energies and the eigenstates. But formally, we are done, but not explicitly. Now, it follows immediately the expectation value of this system at time t will be given by this expectation value. And now I introduce 2 times this expansion with these oscillating phases. I get the double sum of this form with this oscillating phase involving differences of the energies and the expansion coefficients of both psi's and in the matrix elements of the observable. That is everything. That's the equation which governs everything. That's the exact general solution of the quantum problem. In classical physics, we don't have such an explicit general solution. And of course, nothing is lost. It is exact and general. So it respects the time inversion symmetry of quantum mechanics. It's all hidden here. And this is a quasi-periodic function of time. The mathematicians call this a quasi-periodic function with time-independent coefficients here. And they exhibit all these well-known quantum revivals. There exist sufficiently late time points t, where your expectation value comes arbitrarily close to the initial expectation value, arbitrarily often, which immediately implies, of course, that this can be, you can wait as long as you wish. This will never become stationary in any naive sense. This will not converge to anything in the long time limit, unless it is time independent right from the beginning, which is not the usual case. You see all these problems which I mentioned in the beginning, they are of course still here, it is exact. They are all hidden in this equation. And you have now to explain everything on the basis of this equation in principle. So the rule of the game is, I assume that this naive, non-relativistic quantum modeling captures the real world. This is sufficient to describe the real world. And we believe quantum mechanics reasonably well describes the real world, so it will also describe our many-body systems. And in particular, there is nothing more. I need no additional hypotheses, principles, postulates whatsoever. Everything which is needed should be within quantum mechanics, without any addendum. So often in statistical physics, you have a small system which is coupled to one or several environmental paths. And then in such a case, I only deal here with isolated systems. You just think the path and your subsystem of interest is one compound supersystem, which is then, it's again isolated from the rest of the world. So if you have a situation with paths, it is also covered. You simply take the paths into your total model. Now a little bit more technical. We have to restrict the energy of your macroscopic system state. It should exhibit a well-defined energy. Somehow you should exclude Schrödinger cat states, which have macroscopic, not well-defined energies. So for this purpose, that's essentially statistical textbook statistical mechanics. We focus on a so-called energy window of width delta, and we only focus on energies which are accommodated in this little energy window, and we, without loss of generality, let's label them by 1 until ns. S refers to the energy shell S. So these label all those energies in my energy window, and the corresponding eigenstates with these same indices 1 to ns. The span is a sub-Hilbert space called HS, and this is the so-called energy shell. It's a subspace of the full energy, of the full Hilbert space, generated by this. Let's make the microphone a little bit louder. In case somebody is shouting, I should hear him or her. So that's the energy shell. And now I focus on states which are still pure and normalized, which are in this subspace. So I only consider states which can be expanded in this way. I can end here at ns. They are linear combinations. They live in this energy shell. And as a consequence, their whole energy distribution is contained in this little interval. So I avoid Schrödinger cat states which have a macroscopically not well-defined energy. And then, as usual in statistical mechanics, the energy window width delta is assumed to be microscopically large, so a lot of energy are accommodated. The number is very large still, but it is small on macroscopic scales, meaning that all these states has macroscopically well-defined energies. That's the game in statistical mechanics. And the textbooks assure you that all this makes sense. Such a delta exists, which is microscopically large and macroscopically small. And the exact choice of delta is not very important, and all these things are known from statistical equilibrium physics, and typically the number of states in such an energy interval is still exponentially large in the number of degrees of freedom of your system. That's his textbook. And the textbook claim, which we want to understand, among others, if you are in thermal equilibrium, then the expectation values would be described by the trace over the microcanonical ensemble, which is given by the identity or the projector on this energy shell, properly normalized. That's the microcanonical ensemble. And at equilibrium, at this energy, E, the expectation values should assume this value. That's equilibrium statistical mechanics, and we want to understand this. And that's the thing we want now, the precise objective. Now, the first more recent, really new things, so to say, in this new wave on statistics, a new wave of activity in this field, which started maybe 2006, more or less, but actually goes back to the PhD thesis of Seth Lloyd. But it became popular in these two papers. By the way, I will give you in the end the references. Here is it's too short to find them, but in the end I give you the references. The typicality or concentration of measured phenomena. So we sample random states in our energy shell with the property that they are all equally likely. Randomness requires that I give you a probability measure. So all these states, of course, can be expanded in the energy shell. It goes up to NS here in terms of complex coefficients with real and imaginary parts, which are normalized. And being equally likely means that you can imagine this gives rise to a vector of components A and B, and all these components A and B should be uniformly distributed on the unit sphere because they are normalized in R to the 2ns. That means that they are equally likely. You have equally distributed coefficient vectors on the unit sphere. And the main result of these works is this line here. The main result tells you the expectation value of such a randomly sampled state will be very close to the microcanonical expectation value for most of those normalized random states in the shell. And quantitatively, the typical deviations from the exact equality are exponentially small in the number of degrees of freedom of your system, with on the exceptions, the probability that you randomly draw an exceptional psi, which creates a bigger difference here, is also exponentially small in the degrees of freedom. So with extremely large probability, you get an extremely good approximation here. That's the main message of these works. So for the experts only, you can show, you could object, maybe most of these states are unphysical. That would be a natural objection. And within the back of your mind, the requirement that a physical state should satisfy the so-called cluster decomposition property, which means that correlations between local observables, which are spatially far apart with a large distance between each other, the correlation should go to 0. That's the cluster decomposition property. But you can really prove again, the exponential majority of all these states satisfy this property. And in this sense, they are certainly not unphysical. That's only for the experts. It implies first of all, a single pure state can imitate the thermal equilibrium behavior, the microcanonical expectations values, and not even the one single state, but actually the large majority of pure states are doing this. Second, I take an arbitrary but fixed state psi, and now I consider this auxiliary observable A minus this number, this expectation value squared. And then the expectation value of this new observable B psi is also a Hermitian operator. And this you would call the quantum uncertainty of A. In quantum mechanics, that is exactly the thing which appears if you discuss the uncertainties. That's the quantum uncertainty of this observable A in the state psi. Now let's consider another observable, auxiliary observable, A minus the thermal expectation value squared. And then the thermal expectation value of this new observable, you would call in statistical physics the thermal fluctuations of A. That are exactly the thermal fluctuations of A, the mean square deviation from the mean. That are the fluctuations. And now you can immediately conclude from this property, you just multiply everything out, and you observe that this is not only true for A, but also for A square. A square is also possible observable. You can immediately conclude that the quantum uncertainties will be practically equal with these exponentially small deviations to the thermal fluctuations for the overwhelming majority of all these states. So this is amazing. All thermal fluctuations could be explained by pure quantum uncertainties, if you would know and be certain that the world is in such a pure state. It's interesting to note, not only the expectation values can be imitated, but also the thermal fluctuations. And it also tells you the large majority of expectation values is very close to the equilibrium value. That tells you also that there is a small minority of states only which gives rise to notable deviations. So the non-equilibrium states, which do not give equilibrium expectation value, they must be very rare compared to all states. They are untypical, and it is very hard to find them a priori. If you just randomly pick a state with a well-defined energy, it is with high probability an equilibrium state. That's the message of typicality and concentration of measure.
So, Peter, there is a question from the audience.
Yes.
Does this typicality property depends on specific quantum system or it's general? For example, will localization destroy the typicality? This is the question.
No, this is completely general. You don't need any specific property of the Hamiltonian. Yes. You don't have to assume anything more. It's just, maybe it becomes clear from the proof. It is amazing. It's amazingly general.
One quick follow-up, perhaps. Do we assume anything about the observable A? Does it have to be local in some sense?
No, it's completely general. Except that it should have, the norm should be one, or the norm should be finite in case of an infinite dimensional space. I mean, realistic experiments have a finite measurement range, which is the difference between the maximal eigenvalue and the minimal eigenvalue. This should be finite. And then the deviations are, of course, measured in terms of this measurement range. Compared to the measurement range, the deviation will be extremely small.
Here you are assuming, though, that the Hamiltonian is non-resonant, right? There are no resonant.
No, No, it's not. There is no assumption about the Hamiltonian at all.
Oh, right. This is a static. This is a static.
Yeah, there is no dynamic.
Of course. Yeah. Of course. Yeah.
I just randomly pick states out of the space.
Yeah.
But you said there is an assumption that it is non-relativistic. Is it important?
I don't know. I don't know how to model interacting many-body systems relativistically. You can think about it. I cannot tell you anything. I would like to do such an extension, but I don't know how.
Well, you use Dirac equation. Or...
Yeah, but you have many particles and interactions between them and walls to model.
Mm-hmm. Okay.
It is not. That's the rule of the game. We work within a non-relativistic textbook framework. So that's the essence of the proof. The essence is high-dimensional vector spaces exhibit remarkable properties, as you know. The volume of a high-dimensional sphere is highly concentrated within a very thin surface layer of the sphere. This you know. And again, this thin surface layer is concentrated within a very thin equatorial belt or any great circle, and so on. That are these miracles of high-dimensional spaces. And here, it's the same story. Our random vectors can be considered as uniformly distributed coefficients, real and imaginary parts, on the surface of a unit sphere in R to the 2n. That would be this unit sphere. And now you construct, how do we, I forgot, these lines with constant, the surface lines where the expectation values are constant. And for each constant expectation values, you have a set of psi's, which gives you such a contour line. And you have a lot of contour lines, and each contour line belongs to one expectation value. They start here at the poles, and then you have more and more contour lines as you change the expectation value. And one of these contour lines must be at least as big as the equator. But I know the equator contains almost everything. So there must be a contour line which contains practically the whole surface. And that is all. This contour line is practically then equal to the most. Practically all psi's have expectation values very close to the average, because the overwhelming majority has a contour line very close to the largest contour line. That's mathematically, this is Levy's lemma, or the concentration of measure. That is all. Now, as you say, nothing is dynamical so far. Now let's turn to dynamics. There are again some early works, but there are many others. Now let's consider those psi's in my energy shell which belong to some fixed expectation value of some observable. And of course, I take now this expectation value, I assume I take a non-equilibrium fixed expectation value. And then I have non-equilibrium states, and I take them as initial states, and then I propagate them. And if I choose a fixed non-equilibrium expectation value and only take those psi's which satisfy this constraint, then they are far from equilibrium, because this expectation value is far from the equilibrium expectation value. So I have a subset of non-equilibrium states with a common initial expectation value of some observable A. And the main result of these papers here is as follows. It is called Dynamical Typicality, and the main paper is by Bartsch and Gemmer, actually. And it tells you the time-dependent expectation values propagating according to the Schrödinger equation, they will be very similar function of time will be very similar for the overwhelming majority of all those psi's, which serve as initial conditions and have a fixed initial expectation value. In other words, most pure states with similar initial expectation values, this is fixed, given, also exhibit similar expectation values at any later time. That's dynamical typicality. That's again, I mean, it is not so difficult to prove, but I omit the proof. And the same applies if you don't observe this observable A, but you observe some other observable B, which may be different from this A, which fixes your initial value, your initial condition. It applies to any observable. The expectation values for any observable B will look practically the same for the majority of those psi's. And you could also take more than one initial constraint. You could fix the expectation value for more than one observable, and the same story would again be true. And that is, in a way, this explains why experiments are reproducible. In an experiment, you usually only know one or a few initial expectation values of your state, and all the rest is unknown and is not reproducible in an actual experiment. But with large probability, the experiment will behave the same. That's a consequence of this theorem. That's dynamical typicality. They all look practically the same if you know the initial non-equilibrium expectation values of some observables. The future behavior will be practically the same for all of them. But it does not tell you how it will be. The explicit time dependence is not told you. It simply tells you they look all the same. That problem is not solved. So I consider two sub-problems for the actual time dependence. The first is equilibration. Here are some references. I recall, or I introduced the abbreviation AT for this time-dependent expectation values is abbreviated here. And this is given by this double sum, which I already showed you before. That's the solution of the Schrödinger equation and the expectation values. Now, the initial value the initial condition is now arbitrary but fixed. Nothing anymore random, it's fixed. It's a given initial condition, and these are the expansion coefficient, and the AMNs are the matrix elements. I already told you, this is the exact solution. There is no time arrow. Backward in time is equivalent to forward in time. There is no steady limit. There are these quantum revivals all hidden in this formula. Now, for simplicity only, it is not necessary. Let us assume there are no strict degeneracies in your system. And then let me call this the time average. That's the average over all times between 0 and infinity. The long time average is abbreviated like this. And this is easy. You simply have to average each summand. And because they are non-degenerate, all of them will be 0 unless m equals n. And what remains is this sum where n equals m. And Pn are the Cn squared. And they are essentially the population of the n's level in the initial state. These are these Pn's. That's the time average. You can extend this, including the degeneracies, but I omit them here. And now the main result of these papers, you consider how much deviates the instantaneous expectation value from the long time average. square it and take the long time average. So that's the mean square deviation concerning the instantaneous time dependence. And you can show that this is very small under the only condition that all these level populations are small. The sum of them is unity, and each single of them must be small, which is very realistic because no experimentalist can really populate only a few of those levels. That's experimentally practically impossible because these levels are extremely dense. It would, so to say, contradict the time energy uncertainty if only a few would be notably populated. Or you could say, if only a few were populated notably, then any tiny perturbation of your system, if you remove the last screwdriver after isolating your system, you have to remove your screwdriver, and it immediately will destroy this property that only a few of them are notably populated. It's extremely structurally unstable. So this is a very natural and realistic assumption. And this tells you essentially that for the overwhelming majority of single time points, the expectation value must be very close to the time average. Not exactly equal and not without any exception. There are still possible exceptional times, but they must be very rare compared to all times. And that is the solution of this puzzle. This will never go to a steady state, but for practically all sufficiently late times after initial relaxation has died out, and excluding these rare revivals, you will be very practically, experimentally, you cannot see the difference. That's the explanation, that it effectively it goes to a steady state. But not mathematically, but effectively it does it. So, and now the second question, let's assume my system equilibrates in this sense. And then the next question is thermalization and the eigenstate thermalization hypothesis. Here are some of the early references. One of the authors of this groundbreaking words, Maxim Olshani, is here in the audience. I've seen him, by the way. And von Neumann was the first to consider this question. Now, I did not emphasize, here I was back in the full Hilbert space over all the eigenstates up to n. And now I return to the energy shell. I restrict my sum up to ns, because thermalization makes only sense if you have a well-defined energy. Otherwise, it does not even, it will not thermalize. So I consider only states with a well-defined energy, which live in an energy shell. So only states up to ns are populated. And now the question is this long time average, or for most times you are close to this long time average, but is this long time average close to the thermal value? That would be thermalization. That's a different question. And that is now the issue here. Is the long time average sufficiently close to the thermal equilibrium value? A sufficient condition for this approximation is, of course, if every diagonal matrix element by itself is close to the equilibrium value. If this is satisfied, all these a and n's are practically equal to these expectation values. I can take it out of the sum, and this gives me unity, and this is proven. If this is satisfied for all energy eigenvalues in the energy shell, then this follows. And that's the so-called eigenstate thermalization hypothesis, that this approximation is very well satisfied for all eigenstate without any exception. And there is numerical evidence and some heuristic arguments that this hypothesis may be true for many systems. If you have a sum of local operators building up your age, and under some conditions, there is much evidence that this is true, but there is no proof that this is true. And there are known exceptions. For instance, if your Hamiltonian is the so-called integrable system, or if it exhibits sufficient disorder so that it gives rise to many-body localization, then it is known that the hypothesis is not satisfied. But also in recent times, many other counterexamples have been brought up. And it is not even clear if they are, well, it is still under discussion what exactly the ETH says and when it is really violated and when it is satisfied. It's a hypothesis after all. So that is not a proof of thermalization. But what is provable is the following. For many local Hamiltonians and observables, these are the most realistic systems of this type, you can prove a so-called weak ETH. So it is not anymore a hypothesis, it's provable. Namely, that this approximation here is satisfied not for all eigenstates, but for most eigenstates. So to say the mean square deviation from this equality becomes very small, but there may be some exceptions where the deviation is large. This is provable for a large class of systems. It is weaker than the full hypothesis, but it is somewhat similar. It's provable. And then if you combine this proof, this knowledge that the weak ETH holds for certain systems, then for those systems, you can combine this with the previous dynamical typicality setup. So you only consider initial states with a fixed non-equilibrium expectation value of some observable. And then you can prove that most of these initial states will equilibrate. So they will approach a long time steady state in practice, and they will thermalize. The steady state, the long time average will be close to the microcanonical average. This is provable. And this is our own ongoing work at this moment. And by the way, there is not very much which you really can prove what regards thermalization. This is one of the few things you really can prove. That seems very plausible, and it is reason to expect that all this is true, but it is not proven. There is not very much you can prove as far as thermalization is concerned. Now the second thing, in the last 10 minutes or so, I told you now something about sufficiently late times, which can be said. And now let's try to say something about the transient relaxation process before this long time behavior is reached. So the typical time-dependent relaxation, it is all buried already in von Neumann's groundbreaking work, and then Markus Kramer and myself and many others continued with these ideas as follows. I give you, let's assume the initial state is given. It's not anymore random, it is given. But it lives in the energy shell, it has a well-defined energy. The energy distribution is confined to this interval. And it is given. And now, just let us consider the following. You see later why. Let's just, for the sake of simplicity, let us consider the following manipulations. I take some unitary transformation of this energy shell into itself, a unitary operator on the energy shell. And now I modify all the eigenvectors of my Hamiltonian. Every eigenvector is mapped to U times the eigenvector. So it is unitarily rotated in this energy shell according to some unitary all eigenstates are somehow rotated, but the eigenvalues are unchanged. That's the rule of the game. And now I take a lot of such unitaries. I take a whole ensemble of unitaries. Each of them gives rise to a new Hamiltonian with new eigenvectors, but the same eigenvalues. And now the initial state is not random, it's fixed. The random thing which now comes into play are these unitary. I take a random unitary among all possible unitaries so that all are equally likely. That is the so-called Haar measure. I sample, according to the Haar measure, a random unitary among all possible unitaries. And then I do this game. And the main result is as follows. For the overwhelming majority of all those unitaries, it is true that the time-dependent expectation value of A, with this fixed initial condition, the time-dependent expectation value is given by the thermal expectation value plus some function f of t, I come back to it immediately, times the difference between the initial expectation value at time t equals 0 minus the thermal value. That can be said. So the deviation from this equality are exponentially small in the number of degrees of freedom. And the probability, I mean, it's all about probabilities to sample some u. And the probability to sample a u which makes bigger deviations here is exponentially small in the degrees of freedom. So with overwhelming majority, this equality will be exponentially well satisfied. And this function f is given by this expression, the sum over all these oscillating phases, normalized. So essentially, this is the Fourier transform of the spectral density, this f. And you can discuss this function. F of 0 will be 1. And for sufficiently late times, this will be close to 0 for most times, not for all times. It's again a quasi-periodic function. But for most times, this will be close to 0. That means for most late times, this will be 0, and you approach equilibrium value. And and if f equals 1 initially, you have the initial value, of course. This f describes how this goes from the initial value to the long time equilibrium value. So the thermalization is hidden in this f function. And now, in the typical statistical case, let's call omega of E the number of all energy eigenvalues which are smaller than E. So omega counts how many energies En are smaller than E. And the logarithm of this omega times Boltzmann constant is the usual Boltzmann entropy in equilibrium statistical mechanics. And the temperature is defined as the inverse derivative of this entropy. That's how temperature is defined. And now, if you assume, you see this counts, this is an energy counting function, and the derivative will be somehow the energy density or the spectral density, how many levels are in a little energy interval. And that is exactly what you need here, the density of the ENs. And you can imagine if you replace here the sum by an integral over this density, you can introduce this and you can carry out this integral here, and you find f will be 1 divided by 1 plus t divided by this Boltzmann time tau, which is h bar divided by kBt. This can be easily, if you assume that the level density satisfies the usual statistical mechanical relations, you find this here. This is completely universal, independent of the observable, independent of the initial state. That's what it is. That's the prediction. And now comes the usual random matrix theoretical argument. Practically all these Hamiltonians with unitarily rotated bases and the true energy eigenvalues satisfy this relation. So also the true Hamiltonian is supposed to satisfy this relation unless there are a priori reasons why the true ones should be special compared to all these other Hamiltonians with rotated bases and the same spectrum. That's the random matrix theoretical argument. It cannot be proven, but it is very successful in practice, this argument. That's a non-rigorous step. And let's see how it works. So I compare the theory with experiments. For instance, an experiment with ultra-cold atoms in the group by Jörg Schmidmeier. The paper was called Relaxation and Pre-Thermalization in an Isolated Quantum System. So it is about ultra-cold atoms in such a Bose condensate. And what they observed is an observable called mean square contrast, which quantifies the correlation of the matter wave interference pattern. After coherently splitting, initially you have one Bose condensate, you split them into two quasi-condensate, and you measure the wave matter interference pattern. I don't know what this is. That's what they measure experimentally. But fortunately, I don't know. I don't have to know what it is. This can be any observable, whatever it is, I take it. That's my observable. That's what they measure. Of course, it is not, the units are not known. And they have to tell me the initial value, and they have to tell me the long time value, since I don't know anything about this observable anyway. But apart from that, everything is then fixed. The F function is given. The Bose gas has the temperature 5 nanokelvin after it has equilibrated in the long time. And you see, I can fit this observation with my F function. Of course, this is pre-thermalization. It's only, I mean, if you wait long enough, experimentally, it's only pre-thermalization. It will go to a different, truly long time thermal value. Anyway, you can explain such an experiment, or here's another one, a pump probe experiment on ferromagnetic films. So that is magneto-optics in the ultra-fast regime, thermalization of spin population in ferromagnetic films. You observe the relaxation of hot electrons. You shoot a laser pulse onto your magnetic film, and then the electrons are out far from equilibrium due to this shot. And then you observe something which they call differential transmission. I don't know exactly what it is, but I don't need to know it. It is some observable anyway. And you can estimate or measure the final temperature after the hot electron gas has rethermalized, but excluding the interaction with the background crystal lattice. This is, so to say, it is isolated from the lattice. This initial relaxation of the hot electron gas is much faster than the later relaxation where it exchanges energy with the background lattice. And then it is in this sense an isolated electron gas. And that is the measurement. At time 0 is your shot. And the dotted lines are my theory with the F function. It is not so bad here, but it is bad here. And the reason is, of course, this is it is ultra fast, but it is not infinitely fast. These laser pulses have a finite width anyway. And you can, the pulse and the pump laser pulse has a finite width. and the combined weights can be estimated in the experiment, is 15 femtoseconds. And so you, as a poor man's approximation, you just convolute this ideal theory with a Gaussian of this width, and then you get the red line. And this is practically perfect if you include this fact that this is not an instantaneous perturbation, but it has a finite width. And you could, I mean, this is essentially, I think there is no other analytical theory which could explain these experiments. And of course, you have other numerical experiments are, of course, much more convenient even, because then you know the temperature, then you know more things more precisely in numerical experiments. So we also have numerical experiments which can be explained. And of course, we have many numerical and experimental data which cannot be explained by this theory. And we could explain why it does not work. There are these a priori reasons. If this random matrix theoretical argument breaks down, if there is an a priori reason why the true Hamiltonian is not one belonging to the overwhelming majority. This is quite often the case, and then this theory is useless. But sometimes it is useful, and it does work, and it can explain some things. So this is my final summary. So I explained to you to some extent the basic typicality phenomenon. Pure states can imitate thermal equilibrium as far as expectation values of observers are concerned. And their quantum uncertainty imitates the thermal fluctuations. Dynamical typicality, extending these ideas into the dynamical realm. Most pure states with similar initial expectation values also exhibit similar expectation values at later times. That's dynamical typicality, but it does not tell you how they actually behave. It simply tells you they all, or practically all, behave practically the same. And then typical temporal relaxation was the last part. It is a quantitative analytical prediction, which is in good agreement with various experimental and numerical results. And it is in very bad agreement with other results, I should say. No doubt. This does not explain everything, but it explains some things. And many important questions are obviously still unsolved. And now I come to the references. In the unlikely case, you noted those references, and then you can look them up. So you don't have to read these papers, but you can look up the references in these two papers. This is a very nice review concerning the general field of thermalization and equilibration. And this is more or less something like a review on the topics of typicality. And with this, let me conclude and thank you for your attention.
Thank you very much for the great talk. We still have time for a few questions. And first, Maxime, go ahead.
Yeah, Peter, hi. Yeah, first of all, those are, especially the temporal results are absolutely great in studying and in their simplicity. And I have a comment and a question to the very last part. So a comment is that my recollection is that you don't need to go for the full random unitaries, just random permutations of the eigenstates in the microcanonical window would already lead to your results. So you don't, instead of going for the full Haar measure simple random unitary on H, you can just randomly permute the eigenstates, and so it's most derivations become easier.
That's right. That is published, by the way.
Yeah. Oh, okay, okay.
It is hidden here.
Okay.
You can't do permutation and you get the same thing.
Yeah.
And then you cover even, okay. You
Well,
are
I
right.
didn't know.
You are right.
And the question is, I mean, so what happens to the exponential decays? Let's say gas of hard spheres with a disbalance in the transverse. Let's say in X and Y temperatures. I mean, it's known that it decays. The relaxation is exponential. I mean, where is the exponential relaxation? I mean, how can you transit to that?
In these works, there are big sections about where this is discussed. So essentially, if your initial state has a spatial inhomogeneity, that means if you need transport currents during the relaxation process, if there are some other unbalanced conserved quantities which during the relaxation you have transport and then they equilibrate. Then you can show this is one of those a priori arguments which tells you that in this case that was not a good idea. Your true system is different from the majority of these. If the initial state, if you have I mean, these transport currents are in a way almost conserved quantities because, for instance, you have two compartments with different energies and with a small interacting interface. They are almost conserved. It's just an interface compared to the volume. And if you have conserved quantities, then of course you cannot randomly change the eigenstates, because conservation means that you have a common eigenbasis of H and of your observable. And if you start to randomize your eigenbasis, this gets lost. So if you have conserved quantities or almost conserved quantities, that is wrong, because the true system is not a typical system in this sense.
Okay.
And that is, of course, what happens in most real relaxation processes. You have initially some inhomogeneities of quantities which are connected with currents and which have to equilibrate. And these are, that's a different world.
Okay.
That's a complementary. This describes the relaxation within each little subsystem. And then the exchange between the subsystems is the complement, which is missing here.
So in short, are you saying in many physically relevant situations, the central boxed equation is still true, but you have an exponentially decaying F?
No, everything is wrong. This is wrong and this is wrong. It is simply, I mean, this randometric theory argument is simply not true. It is still true. I mean, that's a mathematical statement. This mathematical statement and this mathematical statement is true, but your true system simply does not belong to this overwhelming majority. The last argument is wrong. That's the problem of randometric theory in general. This goes wrong here.
Okay, we have another question by Luca.
Yeah, so I had actually essentially the same question as Maxime, but maybe just as a follow-up, I wanted to ask, so even in the case when your system, your initial state is homogeneous, say in terms of energy, so that there's no transport, it's known that there are kind of higher order transport effects that will govern the late time relaxation of things, like kind of two diffusive excitations. So you would still have kind of like you can't avoid it. Yeah, I guess just from the fact that heat diffuses, in any system that has a Hamiltonian, it's hard. It seems hard to escape. So how exactly do you?
Well, for instance, here is no diffusion. At each place, at each position in space, the electrons are heated far away from a Bose distribution. They are simply not thermally distributed at every place, but homogeneously, and then they have to rethermalize. There is not really a diffusion here. If you have diffusion, I mean, diffusion has to do with currents and transport, I would say. And in such a case, everything breaks down.
So in this sense, your result would be kind of observable dependence in these situations where for some,
I would
things
say
that coupled
it is more initial state dependent. The non-equilibrium initial state must be so that upon equilibration, there will be no spatial currents and no transport is necessary in order that your initial state thermalizes. That's one of the a priori reasons where it can go wrong, but there are other reasons why it can go wrong.
Okay. Thanks.
Are there other questions?
Okay, I have one. So, Peter, you are saying that the system is perfectly isolated, but in real life, you cannot ever have such systems.
Yes.
You cannot switch off gravitational field due to other planets and stars, for instance. You cannot stop the expansion of the universe. So the very space in which we exist is not stationary. So how do you deal with that?
But it may be isolated. I mean, it needs to be isolated, not stationary. But anyway, I mean, if I cut out the part of the whole universe, this is a so-called physical system, it's part of the universe, and I don't take into account the interaction with the rest of the universe. That's an idealization, of course. But otherwise, you could never deal with only a part of the universe, because elementary quantum mechanics cannot deal with systems which interact and are possibly entangled with the rest of the world. There is no way to, the basic quantum mechanical machinery cannot work with such a situation. You have to cut out the part and then apply quantum mechanics to this idealization. You cannot start with your subsystem and taking into account effects of the rest. It's not, you have to include the rest in your model. There is no other way to deal with it. Otherwise, you have to start from a different kind of quantum mechanics, including environmental effects from the beginning. But I think you should not start, you should not take such a Lindblad or whatever it is as a fundamental starting point. I have not a very good feeling to take this as the starting point of your fundamental theory.
Okay. All right, thanks.
Any other questions? Okay, so let's thank Peter Reimann again. Thank you very much, and see you next Wednesday.
Thank you for this opportunity. And I hope to see Misha again soon.
Well, thank you, Peter. Thanks.
See you.
Thank you very much. And let me just add that next Wednesday we have Julian Leonard giving an experimental talk, and he will speak about many body localization under the microscope. So hope to see you all then.
Thank you, and bye-bye.